establish for us here just the mathematical basis of LCI. Okay, it is just spreadsheet math and addition, but I want to express it in a matrix form so that the connections between life cycle inventory, as ISO, the International Standards Organization, does it, what consequential LCI is, and what input-output LCI is, so that those distinctions become very clear. Okay. So this is one representation. We've looked at one form of this already. This is just another, looking at LCI. So you got your raw materials and energy coming in to each of your unit processes across the life cycle. You got your products, your co-products, your emissions, and wastes. And what's exogenous or outside the system boundaries are the design of the product. This is a thing that already exists in LCI. And you're going out and you're making measurements on the unit processes within your system boundaries. So the design of that product is linked, and then the number of units that you're talking about. So we use this example of hand dryers in the restroom, right? And talking about paper towels. And this scaled linearly in the example, right? And LCI is a linear framework. So the quantity demanded is strictly outside. It's not being determined within your system boundaries. Right? So if it's 2 paper towels or 10,000 paper towels, it's just a scale factor difference, and that just lies outside. Okay. So this is LCI as we've talked about it. And if we now try to represent mathematically what's happening here, we can use matrix notation and sort of take the demand, which is exogenous. We've got 10 products we need. Okay. And if we need 10 products, each product uses a kilogram of steel, well, then we're going to need 10 kilograms of steel, right? So you've got some generalized unit process matrix going on here, which might describe how much steel you need per unit product. And then the scale is just going to, scale factor just comes along for the ride. So the demand is exogenous. The technologies are fixed to achieve the demand. And then the scale just scales to the demand. So if it's 1 unit or 10 units or 1,000 units, S changes with the scale. Okay, it's a linear system. Okay, so A is called the matrix of technology coefficients. They're associated with the functional unit. D is the demand. Demand is the demand for the functional unit. And S is the basically dependent variable here. So we would rearrange to solve for S. Right? This is an example. So this is for a vehicle. It's a production matrix. And what we're looking at here is for, just imagine maybe it's an engine in a vehicle or something like that. So one, per vehicle. This is the technology matrix A. Per vehicle now, basically you're going to consume in energy 100 megajoules to produce rolled aluminum. These are 4 processes, right? One is the production of energy called electricity, to produce aluminum, to produce steel, and then to do the machining in the production. So imagine there's 4 steps to produce the engine. It's not realistic, but it's just an example. So to roll the aluminum, I need 100 megajoules, and I need 25 megajoules to produce the steel, and 500 megajoules to do the machining. Some made-up numbers here. In the machining, we're going to consume 20 kilograms of aluminum. And the steel, the amount of steel we consume, just for fun, we're going to relate that to the design here. So depending on the size of the engine, it's going to be 0.1 times the size of the engine in horsepower, just for fun. So you begin to see how we might introduce design variables into an LCI framework by doing that. I'll say more about that in a minute. Or maybe you just assume it's, I don't know, how many horsepower? 500? That'd be nice. Okay, so if I have A and I have D, I'm making 100 vehicles. The technology matrix is always per functional unit, so it's for 1 vehicle. Scale factor is going to be pretty clear what it is. And that just, again, comes from inverting the technology matrix and multiplying by the demand. Right? So far, so good? I can't make you do any of this matrix stuff, so don't worry too much about it. But yeah, I think it's important for us to understand what's actually going on here. Okay, so this is our technology matrix, and here's D. And wow, I don't know where that came from. It's just crazy. Okay, so we can now compute S over here. So inverse of A times D, and we've got our scale factor S. Okay, which is helpful because what we can do now is what we really care about are the environmental emissions, right? So what are the environmental emissions associated with those technologies? Well, we can come up with another matrix, B, that are associated with the processes A that lead to the environmental impact, which we'll call V here. Okay, so that's why we need to compute the scale factor. So let's look at an example matrix of B. So B times S equals V. And let's say that the unit processes for energy, aluminum, steel, and part production, these are quantities of greenhouse gas emissions. So these are grams of carbon dioxide equivalent. Okay, so per megajoule of energy, you've got 200 grams of CO2 equivalent. So this is your, remember we have 4 processes here that I haven't listed at the top here like I should have. But, oh, it's because that's the inverse. They're energy, aluminum, steel, and machining. Those are the 4. Okay, so we've got 4 quantities here. And 50 times the horsepower is the grams of CO2 equivalent per functional unit. Okay, so this is just an example of B. And we calculated S before, so we can multiply B times S to get V. All right, so here is, if we have 100 horsepower, a little bit more reasonable. Quantity here, just inserting that there. That's B. Multiplied by S, I get a number, which is 77,500 kilograms of CO2 equivalent. Okay, that's how it works. It's essentially what's going on, you know, when you're doing all this arithmetic. This makes sense? I don't want to belabor it or go too slow through an example, because we're going to make you do this. But there's a reason for introducing it to you. First of all, so you're aware that there is a mathematical structure of LCI. Second, that it makes it clear it's linear. And that's very important, because most of the systems, product systems, are not linear. And that's just one of the things you keep in mind when you're interpreting an LCI. So far, so good? No questions? Okay, so let's start now expanding the system to get us towards, you know, what we might call an economic integration, something we might call consequential LCI. So what we can do here, well, we can do a lot of things with this system. We can take the technology matrix and we can make it a function of design variables, like we did with horsepower. Right. That's one thing we can do. That's typically not done. But that's one thing we can do. The other thing we can do is we can now, instead of just saying the demand's 100, we can use economic theory, econometrics, to figure out what the demand might really be. Could be as simple as these supply and demand curves you might have seen in Econ 100. Or it might be a lot more sophisticated, thinking about, okay, what's going to be the price that the market is willing to pay for a particular design? So this is the price as a function of X. The willingness to pay is going to be a function of the attributes of that product, Y. So let's suppose this is a car. So it might be the 0 to 60 acceleration time, might be the fuel economy in miles per gallon. So there are ways to do this. So if you extend the system now, and we can do the same thing with B, right? And this is just the A inverse times D to get our environmental emissions. Okay. So this would be an example of a consequential LCI where we're actually changing the design, X, and we're looking not only at how the change affects the environmental emissions associated with the technology matrix, we're also looking at how it affects the demand. Okay? So let me go from an example of a small fuel-efficient car to a large gas-guzzling car. And I can look at, in doing so, how the production processes change, and that's fairly obvious. But as the design changes, the demand's going to change, the price is going to change. Right? The willingness to pay is going to be a function of a number of factors. Think about the price of gas. If the price of gas was $10 a gallon, the odds are that you'd be selling fewer of the big one. If you sell fewer of the big one, there's going to be less environmental emissions associated with the production of the big one. Even if producing the large car and the small car, identical environmental emissions, even if that were true, just by virtue of the fact that you might be selling fewer of the larger cars under the scenario where gas is very expensive, the environmental emissions associated with production, total production, the demand, is lower. Right? And there are certain instances, particularly in sustainability analyses, where we want to understand how the economics and environmental emissions play out together. Right? So we'll be talking more about this as the semester goes on. Okay, so I read this. I think we covered all this. Questions? Besides how to do it, because we need another semester probably to get there. But this is a concept. And the reason to really harp on this is because I talk to people who who claim to know what LCI is, life cycle assessment, life cycle inventories, and they start mixing in all kinds of economic jargon with the LCI jargon, and as if they're talking about this system when they're not. Right? So it's important to be clear about what ISO, the International Standard Organization, ISO 14040, what that LCI is, and how you bring economics in. There's no standards regarding how to do this. And these are sort of cutting-edge methods that are being developed in Europe and the U.S. Right? And we'll talk more later in the term about that. It sounds kind of hard, right? If we try to simplify the diagram, we already saw this picture on the first day of class. Essentially, when we go from an LCI to a consequential LCI, we're changing things within the system. So we're bringing now the quantity demanded and the scale factor, which were exogenous in LCI, within the system. And we're thinking about technology and how technology might affect producer decisions. We're thinking about consumer preference, how they come together in the market, and how they determine the quantity demanded and the scale factor. And then the rest of the system is, the basic math and structure is the same after that. Okay? So this is sort of the big picture. All right? So, it gets at the difference between life cycle design and environmentally sustainable design. They're not the same thing. And this is another point of confusion. So I want to sort of drill it down here. That, again, life cycle design using LCA, typically what you're going to do in a life cycle design is you're going to look at option A, take its life cycle inventory, and maybe get to a midpoint indicator. And you're going to do the same thing for process B or product B. You're going to compare the two. And that's life cycle design. If something, and maybe product B has lower emissions than product A. So you say, well, that's more sustainable. But if people aren't going to buy it, and there are other barriers with respect to its diffusion getting in the way of it being adopted, it's not sustainable. It's not environmentally sustainable. Right? And then we could talk about the social factors on top of that. Just talk about the economic factors here. Right? And typically what we call consequential LCA in the use for environmentally sustainable design, we're talking about usually we're talking about perturbing a system. We're talking about adding a policy to a market, or we're talking about adding a new technology to an existing market, and seeing how the system's going to react. So how does, maybe a, corporate average fuel economy standard affect which cars are made and which cars are sold and how much they're driven? And we're going to talk about that example later in the term. Okay? A lot of uncertainty in both cases. Is this clear? Yeah, Monica?
So, I guess the previous slide, LCI versus cLCI. The LCI is the one that's ISO sanctioned, the other one isn't?
Correct. It's not about sanctioning. It's more about the, you can imagine there are a lot of ways to skin this cat. How are you going to model the market? And what assumptions are you going to make about consumer preference? The number of models we're embedding in this system is not pure accounting. There's judgment involved. And it'd be different for one product than another product. And this method so far has been developed for automotive, but hasn't been tested anywhere else. And that's why I mentioned the CAFE example, the corporate average fuel economy standards, because we have example from there. Other questions? I'll just give you one more picture here. I think this one's reasonably effective. So it's just a third view of our life cycle, looking at materials and energy coming in and emissions and waste going out. And that's what life cycle assessment does. Now, if we talk about consequential life cycle assessment, what we're talking about is some change in the system affecting a change somewhere else. So, for instance, if I buy an LED light bulb and I spend $30 on it versus an incandescent light bulb, there could be, well, first of all, I don't know how many dollars short I am, but I'm probably $25 or almost $30, more out of my pocket, at least in the short run. Right? So there are things I'm not buying with that money, and that may actually further increase the benefits associated with buying the LED light bulb, right? Because on average, roughly every dollar we spend is a half a liter of oil. Just think of it that way. It's roughly at a highest level, right? So taking money out of people's pockets is kind of a good thing environmentally. It's not a good thing, if you think about the planet's perspective. But the point is there's an interaction effect between what we buy, how much we spend, and what we don't buy. You can think about this on the production front too. If maybe I'm fishing, I don't know, some kind of fish. I don't know, sea bass or something, I don't know. And, so I fish all them up. And in doing so, by fishing a lot of the sea bass, now I affect the salmon. I don't know anything about fish, right? But, you could think about production of one thing affects production of something else. Now it'd be a consequential LCA. Right? Interaction effects within these systems. Does that make sense? So LCI does not, the process-based LCI, ISO LCI does not consider that. And the example with the cars that I gave, that's where these two systems interact. So we would call that a consequential life cycle assessment with market-driven design. So there's certain preferences that people have for vehicles. Now I go throw some policy on top of it, so I'm going to raise the price of fuel. Their preferences for vehicles change. Therefore, to maximize their profits, different vehicles are made and sold. Okay. So and you could take that, now and look at, the usual things we look at. What are the new, additional energy or reduction in energy, reduction in emissions associated with that change. Right, so that's this consequential LCA with market-driven design. And clearly you can extend that, if I'm going to lightweight vehicles and I'm going to use aluminum to lightweight them, now there's materials acquisitions and supply chain effects that enter into this. Okay. So, a lot of models, right, it can be done. It's for the patient. You might be wondering whether there's an easier way. And the answer is yes. I'm not going to say it's as good of a way, but it has its utility. And that's the environmental input-output LCI approach. Okay, this is a macro-level, high-level approach to environmental assessment. This is, let's call this a bottom-up approach process by process, modeling the interactions and the behaviors from an economic perspective and how they affect the environment. Bottom-up, process-based. And the environmental input-output LCI is a top-down sort of macroeconomic approach. Okay. And this is Professor Scott Matthews from Carnegie Mellon. Carnegie Mellon really pioneered the use of environmental life cycle assessment using the input-output approach. And this quote nails what it is, right? Would you rather have an approximate answer when you need one versus a perfect answer that you can't get? Again, because of data availability, that's usually what it's about. Or even repeatability, right? This is a repeatable method that gives you a high-level answer to basic questions. Okay, so it's a macroeconomics approach. So we're moving from the microeconomic when I talked about how supply and demand are affected by a change in a system. It could be an input, a price, it could be a policy, to a macroeconomic approach. So there's a lot of just excellent material on the web regarding environmental input-output approach for LCA, and Scott's done a lot of work down at Carnegie Mellon. And we're actually going to take a look at the website that they have here in a few minutes when we go through an example. So you've got a bunch of optional readings, you've got a required one coming up here. But what I want to do here is to give you a sense of what this is. Okay, and it's actually very straightforward. This builds upon economic input-output analysis. So this goes back to Leontief, who did a bunch of work to understand the flows of money between economic sectors and how they're related to one another. So if I put $1 million into the machine tool industry, what effect is that going to have on the steel industry? Right, so dividing the economy up into sectors, including final demand by consumers, to understand how the flows of money operate. Using a linear framework and basically creating a matrix to describe flows between the economy. Right? So that's what Leontief did. And you can think about it this way. So here's a $20,000 car. I'm breaking up the money. And we're talking about economic input-output analysis first, and we'll go to the environmental form in a minute, in a few minutes. So break up the $20,000 into the money spent on the engine, money spent on other parts, the steel, the plastics, even down to the conferences that maybe the engineers went to learn more about a certain technology. Now, I look at that engine in its sector, and I look at, if I spend $2,500 on the engine, how much was spent on steel, aluminum, electricity, etc. These are basically flows into and out of sectors. And you can basically, what has been done by the government is taking the U.S. economy and breaking it up into 480 sectors. Okay. And essentially it's just a big table of sales from one industry into another, final demand from consumers. I'll show you what that looks like in just a second. But it's linear. So in other words, if I have 10 units purchased from sector 2, right, by sector 1, and now that goes to 100 units, right, the flow just changes by 10 times. Even though the technology is embedded within or what's actually being bought and sold is changing, everything flows linearly in this system. Easier to see with a simple example, so let's do that. And when you're reading across this table, what you're looking at are, in this case, reading across, you're looking at sales. So this is sales of goods from service sector 1 into sector 1. Here we've got $500 dollars, let's say, of sales from sector 1 into sector 2. When you're reading down, you're looking at purchases. Okay, so here we're looking at purchases from sector 1 into sector 1, from sector 1 into sector 2. Okay, So this is just a simple, you can think of it as an economy. They're adding here a final demand. So these are, let's think of these as the consumers. 1 and 2 are your sectors. And your final demand, these are the consumers. Okay. How we get the value added is a mystery to us for a minute. I'll show you how that's done in a second. Okay. The total demand, you can think of this as your gross domestic product. If we're thinking about the whole U.S. economy, and we look at all the final demand and we add it up across the 480 sectors, that's your GDP. Okay. So I'll let you absorb this for a second and read it because we're going to use it. I'm going to lean on this hard. Does it make sense what the, you got sales on the rows, purchases on the columns. Got enough time to read that? Okay, it's a little bigger. So what we're going to do now is just add a column and a row. So when I look at the sales from all the sectors, in this case there's 2 sectors, and I add the consumer demand to it, I get a total output. That's over here in the final column. Now, if the economy is a closed system, and you're going to say the U.S. economy isn't, that's fine. Treat it as a world economy then. We'll get to that problem in a minute. If it's a closed system, then the output and the input have to equal. And the input to the economy from Sector 1, if Sector 1 only purchased $150 from Sector 1, and only purchased $200 from Sector 2, but created an input to the economy of $1,000, then it must have had a value add of the difference. So 1,000 minus 350 is 650. So this is the value add of Sector 1 purchasing these materials. Okay, so that gets you the value add. And you can either add across the value added or down the final demand to get GDP. Okay? Wrap your head around that for a minute. Go ahead, Steve.
But if horizontally is sales and vertically is purchases, then I can see how differences like non-symmetry about the diagonal, if you like, produces value added. But what does value added represent?
It represents what these folks essentially were willing to pay for the output. Not just these folks, really all 3 sectors if we consider final demand a sector. So these are, if I take a piece of wood and I buy that piece of wood for half $1, and then I turn it down to make a baseball bat. Somebody's going to pay $10 for the baseball bat. That's essentially what it is. It's some expression or willingness to pay that shows up as a difference between the total output and what's purchased. There's no physics that governs this. It's completely dependent on observations of sales. It's a lot to sort of wrap your mind around. There's reading on this, a lot of reading actually. If you're interested in sort of the mechanics of how the system can be used, but hopefully simple enough for discussion purposes today.
So in the baseball bat example, the value added is the difference in price between the piece of wood and the bat.
Yeah. And of course you have to consider how many bats are being sold and how many purchases. And understanding the value add isn't that important for what we're going to do, but yeah, there is this gap, so I just want to recognize what that is. Okay, so some of the Leontief magic, it's not really hard. The guy got a Nobel Prize for doing something you all do on a daily basis, but it turned out to be a pretty powerful thing. So essentially now, if you take the each of the entries in the matrix, so think of these two economic sectors now, and I've got those 4 cells down here. Just dividing or normalizing the output by the total output from that sector into the economy. So here's xj, so j's are columns, and x are the economic flows, and A is a normalized matrix. So if I have 150 units, I divide by 1,000, I get 0.15. So this is just a normalized matrix. And the reason to do this is now, since it's a linear system, if I change an economic flow by $1, then I've got the normalized flows here. Right? So that's sort of step number 1. And you can think about it, this addresses the Siberia axiom. It's one of the powers of this approach. Remember, so you need a truck to make a truck. So the process LCA, you got to draw these subjective boundaries, and it's kind of tough. Here, what this might say is, to make a truck, you need like 10% of a truck. And, for that truck, you need another 10%. It actually converges out if you work out the math into a very simple equation. Right. So you can basically handle all the flows at once. So this is just visualizing it. Okay, if I have $1 of good number 1 coming out of sector number 1, what's required to produce that dollar value of good 1 is 15 cents of goods from that sector, and about 20 cents of goods from sector 2. Yeah. So that's what this A matrix tells us. And similarly for sector 2. To get $1 out of sector 2, I need 5 cents of input from sector 2, as well as 25 cents of input from sector 1. Okay, and these numbers just flow directly from the A matrix. So this is the slide that basically has a magic on it. There's 2 or 3 slides, I guess, with a little bit of magic on it. But in the end, I think you'll find it straightforward. So if I want to get the total output from sector 1, these sectors here, you basically have sector 1, sector 2, sector 3, sector N. So there's 4 sectors. There are all the other sectors. So if there's 480, then this intermediate input represents the other 476 sectors that are just lumped together. And for our purposes here, you can ignore it. Value add and total input. So if I want to get to the total output, just like we did before, I add up the sum across xij, and then I add the final demand, and I get x1 over here. Okay. So this is just an expression of the total demand, is the demand across the sectors plus the consumer demand. That's what this equation says. Now we assume this is a closed system, so xi is going to equal xj, as we talked about before. And we already defined aij as these unit entries xij divided by xj. Right, so each entry in the matrix divided by its total input to the economy. Yeah, so that's it. So doing this now, xij here equals aij times xj. Right, so I'll just take this xj and multiply it by aij, and I get xij. So you just make that insertion here, substitution. Fairly straightforward. And I can write that in matrix notation. A times x plus f equals x. And that brings us to the Leontief equation, which tells us that if there is a final demand change by $1 or $10 or $100, I know what the changes in the flows are going to be x. So this is a Nobel Prize in the box relating changes in final demand to changes in monetary flows within the economy. Okay, and, you know, I'm just blowing through this, right? It takes a little bit of time to stare at, but it's not really any more difficult than I said. And it turns out you can have a lot of fun with this, and people do. And we will. Okay, this is just a numerical example. This is our Leontief inverse here. I, of course, is the identity matrix, if you remember matrix algebra. So just ones on the diagonal, the zeros everywhere else. This is your A matrix that we've already calculated. So I can take 1 minus A, and then I can take its inverse, use Microsoft Excel. You don't have to go back to high school and remember how to do these inverses. And we're not going to ask you to do it anyway, so don't worry about it. And then you multiply it by F, right? So F, this is the table we had, was 350 and 1700. So if I put that column vector, 350 and 1700, I recover my final demand. But what this does is, you know, you can put whatever F you want in. It doesn't have to be the demand observed in the economy. You can just, it can be $100, it can be $200. So if I spend $500 on a washing machine, and I've got a washing machine sector, right, I can figure out the flows between the sectors associated with my purchases, or my purchase of a washing machine. That'll become clear in a second when I go through an example. Okay, you kind of following this? Not expecting you to be memorizing it, but following it anyway. Questions? It's dry stuff, isn't it? But wait till you get to use the website. It's kind of fun. Yeah. All this stuff baked into this website that Carnegie Mellon created. And it's fun for the whole family. Go ahead.
Could you go to that slide where when you divide each entry by the input to the economy, you said it like 0.1 of that sector contributes to making a product, a good from that sector. I think it's like 3 or 4 slides back. Can you explain that, how it actually works?
How it works?
Like, how can we conclude that?
Can you elaborate what the question is? Because I can't really answer
Yeah.
it. Because you know, it's just a division of 2 numbers, right? I take this one, I divide it by this.
Yeah, and then how do you conclude that to make a good from sector 1, it requires this much percentage from sector?
So you're asking where the data came from?
No, I'm asking how we can conclude from just dividing that.
Well, it's by the definition of what these entries are. So, you know, if I'm looking at this number here, this is the purchases by sector 2 from sector 1. So it is the economic flow. So this is $500, right? So if I normalize by the total output, then per output from this sector, right, it's going to be 500 over 2,000, going to be 0.25. Right, so for every dollar, it's 25 cents coming from this sector. That's what the mechanics is.
In practice, well, I can see how we get the final demand. Like you can see like all the sectors in the GDP. But how do you get in practice the inter?
Yeah, Department of Commerce, just trust them. That's what people do. Their methods to get there, it's a lot of survey data. And you know, the one question you should ask is whether we trust the survey responses. And they do their best, but you know, they're still surveys. So they actually go out and poll the sectors. And each sector has its code. And basically there's sampling of data regarding transactions. And they try to capture all the flows. It's a big job. And they do this about every 5 years or 10 years? I can't remember right now. I think it's every 5 years they do this.
So they capture all the flows between all the sectors.
Yes. And then they populate this for 480 rows and columns. And then the flows into the consumer demand there, too. That's a big job. Other questions? So the Leontief inverse here, the nice thing about it is it normalizes that, the flows for, the year 1997. Now you say, okay, well, if I trust that A matrix, now what if I spend $100 in sector 1? Going back to our example, we calculated the inverse, and now I just put in $100 change in the flow in sector 1, no change in sector 2. I multiply I minus A inverse times F, and I get the magic answer. So essentially $100 of expenditure, additional expenditure in sector 1 leads to basically a growth, if you will, of an additional $25.40 in sector 1 because sector 1 purchases from itself, and $26.40 into sector 2. So the total increase in outputs, the sum of those two, just over $150. This is where the environmental part comes in. So, once, if we can do this with dollars, then why don't we just do this with environmental emissions? So let's go go into the gentleman's question or Jose's question. Well, if we can survey about economic data, why don't we survey environmental data? And we'll do our best. And we'll determine that for every dollar spent in sector 1, 100 grams of hazardous waste are created. And for sector 2, from our example, 5 grams of hazardous waste produced for every dollar spent in sector 2. So if we know the monetary flows, we can multiply with the R matrix and figure out the total generation of hazardous waste. And it doesn't just have to be hazardous waste. It could be global warming potential. It could be energy consumption, anything you want, as long as you have the data. Yes, Steve? No. In fact, you're going to see it as E in a minute, which is irritating. So I'm just using Scott's notation here. So this is our sector 1. As we've seen already, if we have a dollar coming out of sector 1, we're going to require 15 cents from sector 1, 20 cents from sector 2, also going to produce this 100 grams of hazardous waste per dollar. Right? And likewise for sector 2. Okay. So the math of this then just says, if you can calculate, if you have R, you just multiply by the flows, the monetary flows, and you get the total environmental impact. Remembering that R from the first sector was 100 grams, and from the second sector was 5 grams, we just make our R matrix. And this is a diagonal matrix with zeros off the diagonal. And you just crank through. So we know that X is the Leontief inverse times the change in final demand, which we calculated already. So this is I minus A inverse times F. That equals X. This is X. So now I need to multiply this by R, which we do. And we conclude that just over 12.5 kilograms of hazardous waste are generated by sector 1, about 130 grams by sector 2, so it gives you about 12.6 kilograms of hazardous waste. So this is the 30-minute version of how environmental input-output LCA works. And we'll go through an example in a minute, a specific example, not a toy example. Steve? The environmental matrix. You can call it whatever you want. Here, they don't give it a name here. This comes from a book. Environmental discharges as a result of sector output changes, E. We called it R. This is not a standard methodology. It's a methodology that is repeatable because there's only one Department of Commerce set of tables. And EPA and Carnegie Mellon, they've put together some of these environmental coefficients. It's basically only one set of those, so you're only going to get one answer. But it's not a standard. It's not an ISO approach. So the notation may differ. So the nutshell of what we just went over, if we're trying to figure out the overall emissions or discharges, you begin with the change in the final demand for the sector. You then multiply that by the Leontief matrix, inverse here, matrix. Multiply that x by the environmental coefficients matrix, I'll call R. And then you multiply R times X. Sound fun? It should not be fun. In-class exercise. Okay, so grab a sheet of paper or whatever you're going to write on, stone tablet, gum wrapper, and put your name on it, and answer this question. You've got two washing machines that you're comparing. And one is a top loader. It costs $500 to purchase, uses 40 gallons of water per load, and it uses 2 kilowatt hours of electricity per load. The household that we're thinking about, maybe it's your household, 8 loads of laundry per week if you buy that laundry machine. Machine 2 is a front loader. It costs more. And you can double up on the clothes in there. So it has twice the capacity. And it also uses half the electricity and water per load as machine 1. So I don't want you to grab a calculator and start doing algebra on this. I want you to think about what the solution approach is here. We've talked about 3 LCA methods. Given only this information, what would you do? So take a couple minutes to think about that. You can talk to each other.
We don't even have that.
Okay. Preferred methodology, we'll take a vote. ISO-based LCA. Who wants to do this that way? Based on this information. Consequential LCA. You go ahead, don't be shy. All right, handful. And then economic input-output. That's a majority. So how come nobody wanted to do the ISO LCA? All right, so you're not given the data, and you saw a lot of dollar signs here, right? So that was your dead giveaway there. So it has kind of had to be consequential LCA, or it had to be input-output LCA. Now, how would you do a consequential LCA on this? Go ahead.
Well, the inputs here, consequential LCA, your price, and then your performance attributes. So you know the initial cost of each washing machine, but then you can also weigh performance as the capacity of the washer, the energy usage, and the water usage.
Yeah,
do it that
that's exactly right. So if you could construct sort of a supply-demand curve, you don't have the data to do that here, but if you knew what consumer preferences were with respect to price and other attributes of the washing machine, and figure out how many of these might be sold, and then on top of that, though, you'd kind of be stuck because you'd have to go back to the LCA, and you go and say, okay, well, what are the emissions associated with electricity? That's not so hard, right? But where you'd really get stuck is the production processes. There's one thing we haven't discussed yet, and we will talk later in the term. LCAs for manufacturing processes are, the databases are very weak. So you could say in general, very little is known about the emissions. There's studies out there, but it's hard to generalize. But in terms of input-output assessment, what if there was a home laundry machine equipment manufacturing sector? That'd be nice. Then we just sort of multiply by 500 and we'd be all set. So let's think about this from the input-output perspective. This would be your 5-step approach to get an input-output environmental LCA. So you take the total, well, you already know the purchase cost. Machine 1, the less efficient one, was $500. The more efficient one was $1,000. That's a purchase price. Now you break that down, and then you look at the annual costs of water and electricity. Then there is a household laundry equipment manufacturing sector. I'm not making this up. It's a cooked example, clearly. Then you look at the power generation and supply sector. So basically there's 3 things going on here. There's production of the washing machine, and there's a sector for that. There's electricity consumption for the washing machine. There's a sector for that. And then there's water usage. The water, sewage, and other systems sector covers that. So we are ready to go, except we ignored disposal. So it's not a true LCA because we are ignoring disposal here. Let's just make the assumption that disposal doesn't matter. Then we're good to go. And that's basically what this slide says. So let's take a, go ahead, Vinny.
You could use consequential LCA approach here?
Not with the data that's given. If you can do an LCA, if you had the processes listed out, then further, you had some information on supply and demand as a function of the attributes, then you could do a consequential LCA. Or if you had a case where suddenly the industry was regulated, and you had the sort of the life cycle assessment, and you could understand through a model how those regulations would affect which washing machines are produced, which ones are bought, and how they're used, you could calculate the emissions. So you could, but we're not giving you the data to do that. But one thing I didn't say is you can't do a consequential LCA if you can't do an LCA. Right? So consequential LCA is expanding the system boundaries, it's not shrinking them. That doesn't mean a consequential LCA is less accurate than an LCA. It can actually be more accurate. Right? If you just think about the fact that the LCA captures behavior and economics, if you have good models of behavior and economics, it's actually going to be more accurate, all other things equal. Of course, that's not a guarantee. It can be less accurate, too. You have any follow-up?
Either of this model was already in use and you're thinking about replacing it with the other model, then that kind of a situation qualifies for consequential?
Well, you're just comparing A versus B. There's no behavior change. There's no real system change. You're just comparing A and B. And if nothing else changes, then that's just a life cycle comparison. That's all that is. But if something changes, you know, because of suddenly you've got washing machine B, and you know it allows you some function that you didn't have before, and you want to bring that behavior change or system change into the model, then that becomes consequential. It has to be some consequence, not just comparing A versus B independently. It has to be connected somehow. Hence the name. Very good questions. You want to see how this is done? It's fun. It's a little hard to read. Sorry about that. But this at the top is just the table that we went through. So here are the costs. So machine one's $500. It's using 40 gallons per load. There's 8 loads per week. And there's an electricity consumption per load of 2 kilowatt hours per load again. So you can add up the costs. This is kind of fun, right? So here's machine one. And here is your, this is for the annual cost of water. So we're going to input that to the water sector. So you get $33 annually for machine one and $8 for machine two. 8 cents per kilowatt hour electricity cost. The total is about $66 for machine one per year. Machine two is about $16 per year. You add in the production costs, $500 and $1,000, and over 10 years, and they're not using that present value here. This is just 10 years, no discounting. You have about $1,500 spent on machine one and about $1,250 on machine two. Okay. So this is more of an overview. Let's look at these values specifically. Okay, these are the 3 sectors. You have the production of the washing machine, you've got your electricity sector, and you've got your water sector here. So let's input those amounts. Okay, so according to the EIO LCA database at Carnegie Mellon, if you look at $500 going into the household laundry equipment manufacturing sector, then that $500 is going to lead to about half a megaton of carbon dioxide equivalent, half a megaton. And then about, 5 megajoules of energy consumption. This is 0.005 terajoules. Gigajoules. I'm sorry, it's gigajoules. So let's see where these numbers come from. So this is the 1997 database. There's a 2007. I think there's a 2002 also. So just using 1997 to be more consistent with the book. Household laundry equipment manufacturing boom. This is machine number 2. It's $1,000 or $0.001 million. I put greenhouse gases to get CO2 equivalents, and I click run the model. This is fun, right? If I'd just done this, so you wouldn't have looked at that matrix stuff, right? I mean, you do need to know where it comes from. So there it is, $1,000, greenhouse gases, fun with PowerPoint, and there it is. It's 0.81. I'm sorry, it is well, for all sectors, correct? Add them all up. 0.81 megatons of carbon dioxide equivalent, and thankfully this says 0.83, so they're very close. You understand how I did that? I went to the database, and I'll show you another example here. How about the power generation supply sector? So let's look at, we're going to put basically into the, over 10 years, let me choose machine 1 here, $66 a year times 10 years, that's about $660. Okay, so I'm going to put $660 into the power generation and supply sector. And hopefully I'm going to get 7.1 megatons of CO2 equivalent. Okay, so here's $666. And here's the power generation and supply sector. Greenhouse gases again. And we got 7 megatons. Sorry, what was that number again? It was 7.1. Okay. So this isn't magic. It's actually really easy to do. And you can do the same for water, and trust me, it works. So then you add up production, electricity, water, and you get your total greenhouse gas emissions here expressed as global warming potential, which if you go to Sarang's office hours, you're really going to understand that. What that means is it has megatons CO2 equivalent. 8.2 for machine 1, and for machine 2 it's 2.8. Go ahead.
It looked like for the electricity you chose 1997.
Yes. Why did I do that?
I was just going to say because your electricity costs are spread over 10 years.
Yeah, so use 2007. They wrote the book, I forget what year they wrote the book. It was like the mid-2000s. And they used 1997, and I wanted my numbers to match. That was the reason behind that. It's the only reason.
Yeah, I guess, well, to the consistency question
Yeah.
that's last week,
Yeah.
is there any,
Concern with that? Of course. Of
Yeah.
course. That's one of the many concerns, right? So technology systems change. You're going to use this over a period of time, assuming that everything's the same as 1997. Well, what if there was a boom in 1997 and a recession in 2007, and the flows are going to change, and the values are going to change? And the technology progresses, so maybe the environmental emissions have changed too. So clearly there's issues, especially these databases are used. Well, we can get into the challenges of using them. Let me do that. So just to be clear, the environmental input-output LCA, it's industry-wide. It looks at these inter-industrial flows. It takes you about as low as the product system, right? It's a household washing machine. ISO LCA is, yes, it's product-specific, but thinking specifically about the processes, unit processes. So you can think about them actually as being complementary, right? And there are ways to think about this where you could use them synergistically. But this gets to Keith's question. It's Keith, right? Yeah. To Keith's point, I mean, both have strengths and weaknesses. On the input-output approach, I mean, clearly, it's not just the assumed stationary nature of the data. I mean, that's one huge problem. But another is that the economy isn't closed, right? So, where is this washing machine being made for real? And your washing machine, or the one that we would go to whatever appliance store and purchase, right? So when you start now looking at flows across countries, and there are other countries that do this, but it's not around the world, right? So that's a big issue also, and there may be, of course, different standards in one part of the world than the other. But at least if Keith does this input-output analysis and I do, we're going to get the same number. Right, so it's at least reproducible. If we did the process-based LCA, we might make different decisions, both of which might be okay with peer reviewers, but we could get pretty different answers from that. All right, so it's reproducibility. Both have huge uncertainties in them, as we've already discussed. Okay, so I want to end with this idea of hybrid LCA. This is the complementarity of the process-based approach and the top. Let's say the bottom-up and the top-down approach. Now, let's just give you a visual here. So here's our cutting fluid example again. You remember we left various things out of our process boundary, right? We left tools out. We let work pieces out, right? We certainly left the machine tool construction out. We could add them using the input-output approach, right? There's no reason, as long as you have a clean break between your unit processes, you're certainly allowed to take some information from input-output tables, which may be better than doing nothing. And sometimes you have to do nothing so you don't have the data. And you can add that to your process-based LCA. So that's called hybrid LCA. Okay. So you begin to see how we can bring economics into the picture to bring us towards sustainability analyses.